Started with velocity analysis. I'll quickly go through and take us to the place where we stopped. So the problem of velocity analysis is what is laid down here. We are given the mechanism parameters, both the fixed and the positions of the mechanism, that is the joint parameters or position of every link, and we are also told at what velocities the joints are moving, so which essentially amounts to the first derivatives of the joint variables. We need to determine the velocity of every link of the mechanism. Now velocity of a link in space, of a rigid body in space, can be specified by 6 parameters. If you take any point on the body, then the velocity of that point, the linear velocity of that point with respect to some reference frame, let's say. And then we can define something called the angular velocity vector for that body, which is a 3-dimensional vector. And once we have these 6 parameters, we can obtain the velocity, linear velocity of any other point on the body using this relation. The linear velocity of any point B on the body can be obtained in terms of the velocity of the point A and the angular velocity using this expression, where this is the vector cross product, the vector product, that is the cross product. Fine. What about the angular velocity of any other point on the body? A point doesn't have angular velocity actually, so statement itself is wrong, right? The body has angular velocity, point has linear velocity. Right? Now we started doing this calculation, and that is done in the traditional way, that is the manipulator is represented by these segments P0, P1, P1, P2, P2, P3 up to P5, P6, where P0, P1, P2, P3 etc. are the origins of the reference frames we fixed on the links. Fine. So we get the vector P0, P6. We are trying to now obtain the linear velocity of the point P6, which is on the 6th link, which is on the last link. Okay. So basically the rate at which the vector P0, P6 changes with time, that is what we are trying to obtain. So that can be obtained. This particular vector P0, P6 is made up of these separate vectors. So add them up. So when we take derivative of this vector R P6 with respect to P0, we take derivative of all these vectors. Remember, these vectors are represented in the global reference frame, or expressed in the global reference frame. Okay. So that is implied here. I don't put an extra suffix to clutter up the equations. So now these vectors, since they are represented in the global reference frame, they can be expressed in this fashion. For example, P5 to P6, that is R P6 with respect to P5, can be obtained from the local, the 6th reference frame representation of that vector, pre-multiplied by the rotation matrix, which takes any vector, free vector, from the 6th reference frame to the 0th reference frame. Right? So that is how each of these vectors can be expressed. So now when we take derivative of this particular expression, we need to take derivative of each of these rotation matrices. These vectors are now expressed in the local reference frame, and so they are fixed quantities, so they don't have time derivative. So the time derivative is 0. So we don't have to take separately the time derivative of these vectors. Okay. So, when we differentiate this with respect to time, this will be simply the dot product, I mean the time derivative of this matrix into this fixed vector plus the time derivative of this matrix into this vector and so on. So, we will have this general term, general operation of taking time derivative of a matrix, rotation matrix of this form, rotation matrix which takes vectors from the kth reference frame to the 0th reference frame. Okay. That itself is a chain of rotation matrices multiplied together, and so when we take derivative, we use the product formula, right? That is, if you take two scalars, then the time derivative of u multiplying v, where u and v are functions of time, is u dot v plus u v dot. Fine. We use that applies in this case too. Okay. So, if we do that, then this becomes this particular sum of terms, each term, the ith term involving the dot product, the time derivative of the rotation matrix I with respect to I minus 1. Okay. Sum up all that, you get this particular time derivative. Right. So, yesterday when we finished the class, I asked you to explicitly take that time derivative. Did anybody get to an answer there? If you wait long enough, you know that I will start answering. So, that is not good enough, you should answer yourself. Okay, let us now look at this, the time derivative of rotation matrix I with respect to I minus 1. So, you know that rotation matrix, we had derived the expression for that. So, I will just give the time derivative, you can verify this. The whole thing multiplied by the time derivative of theta I. So, if we take time derivative of that rotation matrix, this will turn out to be this expression. So, now it turns out that this particular matrix that you have here, if you look at each of these columns, then they turn out to be of this form. Again, this is something you should verify. That is, the first column is the cross product of the unit vector along the xi axis and the unit vector along the zi minus 1 axis, right, both expressed in the I minus 1th reference frame. Turns out to be that. The first column turns out to be that. Second column, the same unit vector zi minus 1 with respect to yi unit vector, again this in I minus 1th reference frame, and again sorry, this is z. Now this is not 0 because these are two different vectors, right? The angle between them being that alpha. So this matrix turns out to be this. Now this can be expressed as, this can also be seen to be, fine, this particular, the following matrix. Is a skew symmetric matrix multiplying, yeah, this vectors, a matrix made up of these vectors. So that is R I with respect to I minus 1. Fine. I will call this particular matrix, this is a skew symmetric matrix, I will call this matrix Z I minus 1 cap and put a matrix symbol around that. Okay. This is useful, instead of considering it as a cross product, initially I consider it to be a matrix pre-multiplying this rotation matrix, and then I will revert back to this cross product later on. I will come back to the cross product later on. So the important thing to realize is the following. See, finally, if you look at it, when we substitute this back into the equation, there is a vector which will multiply, post multiply this. So if you take up to this term, it turns out to be a vector, the whole thing turns out to be a 3-dimensional vector that gets pre-multiplied by this 3 by 3 skew symmetric matrix. It is equivalent to taking the cross product of this vector with the vector you are going to get later on, and both these things are the same, are equivalent. So let me now do that substitution. What I mean by substitution is this: we put this particular thing back into this, and where does this go? This goes into this, fine, in all this. So all of them are post multiplied by these vectors. Okay, so substituting it back. Or before substituting, let me do some simplification. So we were taking the time derivative of we were taking the time derivative of this, and one of the terms in that was the time derivative was the following term. This turns out to be so consisting of terms like this, fine, and this gets post multiplied by this particular vector r pk with respect to pk minus 1 in the kth reference frame. Okay, so let me just add that. This is in the kth reference frame. Let me read it out if you can't read. This is r pk with respect to pk minus 1 in the kth reference frame. This whole thing is, we are taking the time derivative of this whole thing, which amounts to taking time derivative of this and multiplying with this, and the time derivative of this is what I have written here. So the whole thing is multiplied with r pk with respect to pk minus 1 in the kth reference frame. So each of these terms then will get multiplied with this. So if you look at one of those terms, so let me retain this summation. And now I will substitute for what we just now derived for this. If you remember, we just derived a form for this. Fine, I will do that substitution. This expressed as this skew symmetric matrix multiplying Ri with respect to Ri minus 1. So this is this term, and so on up to Rk with respect to k minus 1, and this whole thing multiplying now. Let me take this in, and then let me collapse these things, and also these rotation matrices. We get the following. So this rest of the rotation matrices here multiplied turns out to be simply this, and then you have this skew symmetric matrix. Now the rest of the matrices here, and then this multiplied with this, turns out to be R pk with respect to pk minus 1, that segment, yeah, in the I minus 1th reference frame. Fine. Now I shift back to the cross product because it's easy to see to do the algebra there, remaining algebra there. Now this I write, now this is a vector, this is a matrix. Instead of that I write it as multiplication of two vectors, cross product of two vectors. So cross product of this vector with this vector, both expressed in the I minus 1's reference frame. So finally what we get here is that each term here, or rather the ith term here, is of this form, right? Cross product of two vectors expressed in the same reference frame, pre-multiplied by a rotation matrix which takes vectors, free vectors in that reference frame to the global reference frame. That is, these are free vectors in the I minus 1 reference frame, cross product of two vectors. So let's consider the global reference frame. And this is the ith reference frame, I minus 1th reference frame. Take two vectors here, take cross product of these two vectors and then express that in this reference frame. That is what is being done here. The answer is exactly the same as taking cross product of these two vectors expressed in this reference frame. These vectors separately expressed in this reference frame and then taking cross product. Fine, this is the same. So I can write this as, yeah, I actually did not write one particular term out here. When I made the substitution, I missed out one term. Let me bring that back. The time derivative of this had this theta I dot, which I had missed out in the substitution. Fine. That is appearing here, but further on it was missed out. So theta I dot is there. Okay. So when we do the substitution, we need to retain that. So there is a theta I dot involved here, but this is Ri dot, there we needn't worry. But once we get this form, there is a theta I dot here. Fine. It's a scalar. So you can multiply later on after all the matrix multiplications. So here the theta I dot is there. Fine. So put that back. So then come back to what I was saying. Multiplication of these two cross product of these two vectors in this reference frame and transforming it to the zeroth reference frame later can be obtained by transforming each of them first to the zeroth reference frame and then doing the cross multiplication. Okay. So this turns out to be this vector I minus 1 in the zeroth reference frame. Take cross product of that with this segment. Again, this now is expressed in the zeroth reference frame. and theta I dot. Fine. So now what we need to do is put this back into our the velocity expression for the velocity of the point on the last reference frame that we are trying to obtain. That is what we started with. Right? We need to put it back there. But this has now become fairly simple. So over I. So if we go back, we were trying to obtain an expression for this particular point, the velocity of this particular point. Okay. And while we were doing that, we found that we needed to take derivative of this. Having found an expression for the derivative of this multiplied with the corresponding segment, we now put those expressions back here. Right. So when we do that, so that is the time derivative of any term like this is of the following form: I is equal to 1 to k. So the kth term inside this bracket after we take derivative is of the following form. Okay. So if you substitute it back, you get the following. The velocity of the point P6 with respect to P0 in the 0th reference frame. P6 with respect to P0 in the 0th reference frame then turns out to be the following. So the whole thing has acquired a fairly simple structure now. One moment, 6 with respect to P5. Take this term alone. This is the linear velocity of the point P1. This is the linear velocity of the point P1. Take this and that thing. That is the linear velocity of the point P2. So if you take all the terms up to here, what you get is the linear velocity of the point P5. Okay. So what we have is the linear velocity of the point P5 to P0 in the 0th reference frame plus this particular term, fine, which I will retain like that. And take cross product of the position vector from P6, P5 to P6, that is P6 with respect to P5. This is of the form, if you remember, velocity of a point on a rigid body can be obtained from the velocity of another point on the rigid body, and take plus the cross product of the angular velocity vector with the position vector from the reference point to the current point. So this is nothing but, so basically velocity of the point P5 plus angular velocity of the sixth link cross multiplying the vector from P5 to P6. So in this serial chain, the angular velocity of the kth link, this is a vector by the way, is obtained very easily. Theta k. Remember, Zk minus 1 is the axis along the kth joint. Okay, the way we set up reference frame, Zk minus 1 axis is along the kth joint. That is why it multiplies the kth angular speed. Okay, the angular the derivative of the joint angle of that particular joint. So we get an expression for omega, omega 6 also can be obtained, and we get an expression for the velocity of the sixth link and the velocity, velocity of the point P6 on the sixth link. So velocity of the point Pk on the kth link also can be obtained. This is the partial sum of this, that is the partial sum of this, right, the kth partial sum. So only in understanding that it is useful to actually club a few things together. So this P6 with respect to velocity of P6 in the zeroth reference frame can be obtained also in the following way. What I am going to do is, in each of these terms theta 1 dot is involved, right. In 5 of the terms theta 2 dot is involved, in 4 of the terms theta 3 dot is involved, and so on. I club terms in those specific thetas, and then we can write the following. This cross product of a set of vectors which, so R P1 with respect to P0, all these segments, P2 with respect to P1 and so on up to R P6 with respect to P5, plus similarly for theta 2 here this term will not be involved, the remaining terms will be there. And so on up to the last term theta 6 dot I can write this as it's mainly algebra done a little systematically. You will arrive at this clearly. So I club all this together. This is when I sum up all these vectors, I get R P6 with respect to P0. If I sum up all this, I get P6 with respect to P1. This for a physical interpretation, which will immediately make you understand the physical import, how exactly the linear velocities get generated. Can be interpreted in a few different ways. This is a useful interpretation. And remember, all the vectors involved here on the right hand side are expressed in the zeroth reference frame. Fine, you have to remember that, which actually takes us to a generalization, but I will come to that. Before that, let me go back to the picture that we have and interpret this particular equation. So if you come back to our original picture, this first term you can imagine as follows. This is the linear velocity imparted to this point by holding all these joints as rigid, as fixed, and rotating only this joint. Right, with an angular velocity theta 1 dot. So this term arises like that, right. What about this term? Hold all the joints except the second joint fixed and move the second joint with velocity theta 2 dot, remaining with the rest fixed, right. The linear velocity imparted to this particular point through that exercise is this term. And so on. So each of the common linear velocities that you get here, vector velocities that you have on the right hand side, by clubbing the expressions like this, can be physically interpreted like this. They correspond to these physical operations of holding all joints except one fixed and rotating that joint. Fine. So this is an important picture to have in mind. Okay. So finally, the velocity of this turns out to be physically very easy to obtain. All you need to do is, one by one, you move a joint keeping all the others fixed. The velocity that you get out of that is the linear velocity that you get for the point. Now this is true whether the joint is revolute or prismatic. It holds, and it can be shown that it holds. Okay, now we have got an expression for angular velocity and linear velocity. Now we will put that together into finally the expression for the velocity of the end effector. The velocity of the end effector consists of two separate terms, or velocity of the kth link of the serial chain. Expression for so let's put the linear velocity first. And then the angular velocity. Put all this into a single vector. How many elements does this have? 6 elements, 3 for this, 3 for this. So consists of this then. This is the first column. The second column is going to multiply the vector theta 1 dot, theta 2 dot, and so on. And then the last. So this matrix multiplying theta 1 dot, theta 2 dot up to theta k dot. This gives both the forward and inverse relationship that we want. That is, this expresses the velocity of the kth link in terms of the joint variable derivatives up to the kth link, up to the kth joint, right. Rotation you give to the later joints does not affect the kth link in a serial chain. In a parallel chain it is different. So this is called the Jacobian, different from what you talked about yesterday. So k could be 6, that gives the full Jacobian. Why is it called the Jacobian? That comes from the following. If you have a function of, if you have say m functions of n variables, the first order partial derivatives of this with respect to the variables is called the Jacobian, right. So first order partial derivative of f is called the Jacobian. There is nothing but that. right? If you have the position of the kth link as functions of these thetas, position is represented by 6 parameters, right? And they are functions of the thetas. So that is why this is called the Jacobian. Now this for a serial chain with revolute pairs. There are some very important conclusions that can be made from this. Remember, the elements of the Jacobian, the columns are nothing but this 6 element columns are very simple to obtain, right? They are nothing but this these unit vectors along the separate axis, and the cross product of the unit vector along those axes with some particular vectors. Okay, since all this can be obtained by forward kinematics, if you have thetas, you can immediately obtain all this. So you can write the Jacobian very easily. You don't have to go through the derivation which was done right now. All that you have to know is this. Okay, and this comes from a very simple physical picture also, right? The angular velocity is simply the sum of the angular velocities you get from these individual rotations. Okay. Okay. The further one of the important information that we get out of this is the following. In various positions of the manipulator, remember these are functions of the position. Okay, at various positions of the manipulator, what is the ability of the joints to impart velocities in all directions that you want? This is a very important issue. It relates to capability of the manipulator in moving in various directions and in applying forces in various directions, right? So all that can be obtained out of this particular Jacobian. And I said this is the forward relationship, inverse relationship is also right there. If this is a square matrix and if it is invertible, then this can be obtained by pre-multiplying this with J inverse. That is if J inverse exists, right? So all this can be, so the inverse relationship is also right here, the forward and inverse. That is why I did not separately define the inverse velocity calculation problem. Okay, so now in the next class, which will be the last class for kinematics, we will see those physical interpretations, see how we can get the relationship between static forces from the same relationship, and maybe see how acceleration relationship can be obtained. We won't derive that, but we will indicate how that can be obtained.